let's grab some immediate properties of these definite intervals. So number one, notice that this delta x is necessarily positive. Well, typically it is, because I typically think of b as being larger than a, and is a positive natural number. But if the output of my function is negative, that product can be negative, which means if all the values of y over there from a to b are actually negative, this could give me a negative value. For that reason, we sometimes say that this doesn't necessarily give us the precise area of a curve, should I say a precise area of a region, not a curve. But technically speaking, it gives us what I refer to as signed area. If the curve was entirely below the x-axis, that'll be negative. If the curve was entirely above the x-axis, that'll be positive. Or maybe I got a combination of negative and positive values. Sometimes they even cancel themselves out. We'll talk about that soon. Some basic properties of them. Given that we have signed area, if this is true, then certainly this is true. If this is a relationship between two functions, there, then it certainly is the case oh shoot. The next one's a bit tricky. So give me a moment. Let me grab some more. We'll come right back to number 3. Let's concentrate on this graph as x ranged from a to b. And let's concentrate on the evaluation of double integral, which is the area you see shaded in black. Now, if this function's continuous, then over a closed interval, it's going to attain a maximum y value. How about right here? And let's close up maximum y value m. It's also going to hold the minimum y value. Let's call that n. Then wouldn't you agree that the area you see shaded black is the area that's greater than what you see in red as a rectangle, and less than the area you see in blue as a blue rectangle? But the area of the rectangle is length times width. The area of the blue rectangle is length times width. And so I think I've just visually concluded that as long as f of x behaves as such for all values of x in there, then it's certainly going to be the case that the area underneath the curve from A to B is below that blue rectangle. Shoot, I just can't, I don't have enough room. Do you mind if I write backwards because it's easy for me to determine how much room I have? Here is the area of the big blue rectangle, and that bounds above there underneath the curve. But it is a case that that's bounded below by the area of the smaller rectangle. I apologize if that's a little sloppy. But if this is true for all values x and ab, then necessarily that's going to be true. Now, to give myself more room, getting rid of this. I'm hoping you can visualize this in your head. If c is just a constant, then I think what this is really representing is the area of a rectangle whose length is c and whose width is b minus a, or vice versa. And the area of any rectangle is length times width. Now, if you view this as a limit of Riemann sum, then certainly that constant coefficient C pulls outside the limit, so it's certainly going to pull outside the definite integral. And just one last quick property. Again, going back to our properties of limits, certainly the definite integral of the sum of these two beasts in the integrand's position can be interpreted as the sum of these two definite intervals. Matter of fact, that last example, I've already exploited those individual properties. I was hoping that was okay simply because we're interpreting them as limits anyways, and we already have our limit laws down.